Assalamualaikum and hi, today we'll be talking about a numerical methods. So my name is Nurul Shahira binti Harmizi ATP. My number metric is DN240116.
And my name is Wardina Natasha binti Haminova and my metric number is DN240158. So we will be talking about this content, which is introduction, technical and theoretical description, problem solving, and also result and discussion. So for introduction, Newton's law of cooling show how it used to model heat loss and predict temperature changes over time. It introduced two numerical methods such as Euler method and Rouge-Kutta for solving the related differential equation. Euler's method is simple but less accurate, while Rouge-Kutta is more precise and stable, though more computationally expensive. So the study aims to determine which method is more effective for solving engineering problems involving initial values.
So the technical and theoretical descriptions, according to the Newton laws of cooling, the rate at which an object cools is proportional to the temperature differential between it and its surrounding. So where T is represent the object temperature at time, Ts is the surrounding temperature, and the K is a positive constant based on the object properties and environments. The solution to this equation shows that the object's temperature changes exponentially over time. So the greater the temperature difference, the faster the cooling effect. So the application of this Newton law is like forensic science, the time of death, then the engineering like heat and transport modeling, so like everyday coolings, like hot drink coolings. So next, for the Euler methods is a simple numerical technique to approximate the first order of ODE of the form. So this is the first ODE form, then this one is the update formula one. So the accuracy is the first order, the error is proportionally to the step size, where the error will increase when the step size number is increased. So they use the slope at the current point to estimate the next value. The Euler method is very simple and easy to implement, but it has a limitation. So assume the constant slope over each step. The less accurate for the large step size or rapidly changing the functions.
Next, for fourth order Rouge-Kutta method is a highly accurate technique for solving first order ODEs. So it estimates the slope at multiple places inside each step and average them to obtain a weight slope. This gives a much better approximation of the solution. So it computes 4 slopes per step. We have K1, K2, K3 and K4. And then the next value is computed as in one equation which we combine all the K's. And then average slope for better accuracy. Fourth order accuracy is equal to error proportional to h to the power of 4 and more precise than Euler's method, especially for small step size. Next.
So for the problem solving using a manual calculations, first we use the Euler methods. Then the problem statement is a cool drink is poured at 10 degrees Celsius. After 2 minutes of sitting in a room, its temperature is rising. So we list out the information. It gives that initial temperature is equal to 10 degrees Celsius, the ambient temperature is 21.1 degrees Celsius, and after 2 minutes is equal to 13.3 degrees Celsius. So we use the dt over dt equations, and then we use the analytical solution to Newton law to find the constant k. We need to find the constant k because in the equation it didn't state the k, so we need to find it first. So we insert into the t equations is equal to Te plus T initial minus T ambient times with the exponent the power of negative k times T. So we insert all the value inside the equation and find the k value. So we get the k value is equal to 0.1806. After that, after finding the k value, we can apply the Euler methods. Then for the Euler methods is the equation is Tn plus 1 equal to Tn plus h times to the function of Tn minus the Ta. So insert all the informations. We want the step size is in 1 minute, so every minute we want to know what is the temperature rising. So after that we insert all the value, and then we find the T1. T1 is equal to 12 degrees Celsius. So the first T initial is 10 degrees Celsius, the T1 is 12 degrees Celsius, and the T2 is a 13.3 degrees Celsius.
So for risk method, the problem statement is the same. So we have the initial temperature, which is 10 degrees Celsius, and ambient temperature, which is 21.1 degrees Celsius, and after 2 minutes it will become 13.3 degrees Celsius. So the equation is the same as before, and we apply the analytical solution to get the K value, which is 0.1806, and then we apply the Rush-Coulter method, which have four equations, K1, K2, K3, and K4. And to find the values, we insert all the values given, H, the initial and Q into the equation, and for K1 we got 2.0047, and K2 we got 1.8236, K3 is 1.8400, and K4 is 1.6724. And to find the T1 values, we insert all the value of K1, K2, K3, K4 into the equation, and we got 11.834 as the temperature for T1.
So problem solving using a coding, we just insert all the value we get from the manual calculation, we insert into this coding, but the difference is the number of time. From the manual calculation we only calculate for 2 minutes, but for the coding we use for 10 minutes, so we got all the temperature rising for each minutes.
So next for problem solving which involve coding for Rush-Coulter method, it's also same with the Euler method. We insert all the values that we already got from the manual calculation, which is temperature initial, temperature ambient temperature, K constant, H, and also the number of steps is 10 because we want to see the difference between each minute. And we got the temperature for each minute.
Okay, next. So for result and discussion, we plot the graph temperature versus time for the Euler method. So it's conditionally stable, which only accurate with a small step size h. So it's not suitable for the higher step size to use a Euler method. So larger h may cause the unrealistic result, example like temperature overshooting ambience. So it will capture the general exponential decay trend, and then the trend to slightly underestimate temperature at the each step. So next.
So for Rush-Coulter method, we plot the graph also, and this graph shows a drink is warm from 10 degree to 21.1 degree Celsius. So for Rush-Coulter method, it accurately models to exponential warming trend. So it has no instability. Examples for overshooting or oscillation, even with fewer steps. And it captures the steep rise in temperature initially, then gradual approach to room temperature. So for Rush-Coulter also used for slope estimate per step to ensure the high precision and stability. And unlike Euler method, Rush-Coulter stays accurate with larger step size. So it is ideal for showing dynamic changes, especially in early rapid warming phase.
Okay, that's all from us. Thank you.